So the transshipment problem is a type of transportation problem. Let's say I've got the source and I've got the destination and some intermediate node, let's call it I. It is a type of transportation problem where your goal is to ship from S to D in as cheap or as fast as possible. So you're trying to optimize a certain criterion, let's say time or cost. So the cost from going from S to D by passing through I. So this arises a lot in decision making, operation research, and where you have to pass through an intermediate source I'm going to give you a very nice example. You're going to fully understand the transshipment problem through a simple example. So this example is going to contain some, let's say I've got some plants or certain industry. So I've got 3 plants. Those plants, they transport goods to, let's say, a warehouse or multiple warehouses. So I've got 2 warehouses. So those companies or industries, they have a deal with some warehouses. They transport their goods to the warehouses. So they're supplying. And the term supply here is really important. Now, in turn, the warehouses have to supply directly to dealers, or let's call them, in this case, customers. Let's say I've got 4 customers, and the warehouses supply the customers upon demand. And demand is another key term here. So we've got supply and demand going on. And this transshipment problem, the industry is not going to come and sell you, the dealer or the customer, directly. No, it transfers to warehouses, and then the warehouses will supply you, the customer. So what we have right here is just, you can see it as a multi-transportation problem that is seen as one network or one system, right? Because, plant to warehouse is one transportation problem, and warehouse to customers is another one. But you can't just optimize each one separately. No, you have to take both as a batch, as one problem. Note that you can also extend the layers, so customers could also sell to other customers or to shops or so on. So this could be a multi-layer transportation problem, and thus the name transshipment. So we need not to have only one layered intermediate node, right? So as in the transportation problem, each path comes with a cost, right? So let's say for that, the cost from going to, plant 1 to warehouse 1 is 4. From going to plant 1 to warehouse 2 is 7, and so on. I'll just throw in some random values. Likewise, the warehouse has to pay for each path taken to arrive at a certain customer. So for that, let's say this is 6, this is 4, this is 8, this is 4, this is 3. So let's say I've got all those costs, right? And let's put them in a table, right? It looks way better in a table. Right, so we have just tabulated the costs we have at each transportation. The way we can read this is the cost from a plant to the warehouse. So this data right here should be warehouse. So the cost going from, let's say, plant 2 to warehouse 1 is 8. So 2 to 1 is 8. The cost going from plant 3 to warehouse 2 is 6. 3 to 2 is 6. And likewise, if we look at the second table, we've got the cost going from a warehouse to a customer. So let's say the cost from going to warehouse 2 to customer 4 is 7. 2 to 4 is 7, right? Now, what is the total cost of this, let's say, system? It's the sum Cij Xij, where Cij is the cost, which is extracted from this table, from plant I to warehouse J, whereas Xij is the number of units that I am transporting. So you can understand it that way. One Xij will cost you Cij. Right? So you can put it that way. Now we've got an I going from 1 till 3 because we've got 3 plants, and J going from 1 till 2. Now we've got to add the other cost as well, the cost from going from the warehouse to the customer. So we've also got a double sum. It's the same thing, but I'm just going to change the notation a bit. So I've got Cij prime and a Yij. Okay? So my I is going from 1 till 2 because I've got 2 warehouses. So Cij prime is the cost per unit from going from warehouse I to customer J. Likewise, Yij is the number of units being transported from warehouse I to customer J. So for that, my J will go from 1 to 4. Right, so in case we want to expand this, you could just copy paste the values right here. So I just replaced the values and I just colored the cost from going, the total cost from going from the warehouse to the customers in blue. So this summation right here is nothing other than this part, right? And this summation right here is this part, okay? I'll just remove the markers because it's making stuff look really weird. Right, so this is the total cost from transporting goods from the source to the destination, from the plants to the customers. Now, as one might suspect, if we leave the problem as such, unconstrained, right, no constraints whatsoever, and your objective is obviously to minimize this total cost with respect to my x's and y's, the solution is trivial, right? It's just all zeros, so everything is zero. That means I'm not going to transport any goods, right? Because that's what you have. You want to minimize the total cost? Well, there you go. Don't do anything. Don't transport anything. But life doesn't work that way. So to model reality, we're going to have to say some stuff about the plants and the customers. So let's say the plants have a certain capacity, right? Plant 1 could not produce more than 450 units, for example. 450 units. Plant 2 couldn't produce more than 600 units, and Plant 3 couldn't produce more than 380 units, right? So I've just added this column right here. Each plant has a certain capacity. And likewise, let's say customers there's a certain limit on their demands, right? So the plants are supplying with a limited capacity, and customers are demanding under a limited threshold. Let's say the customer 1 is happy with 300 units of goods. Customer 2 is also happy with 300 units. Customer 3 as well. And customer 4 is a bit greedy. He's got more clients, so he's happy with 400. And, customers are always right. Those should be modeled as equality constraints. So the customer doesn't need less or is not happy with less, and, he doesn't need more. He needs the exact amount, 300, 300, 300, and 400, okay? Whereas plants, you can be flexible with plants. You can model plants produce at most 450. Plant 1 produces at most 450 goods. Plant 2 produces at most 600 goods. And Plant 3 produces at most 380 goods. So let's add this data to the customer table. So this is how the tables look like right now. Let's translate capacity, first of all, into constraints. The first constraint we can put on Plant 1 is that the total number of goods produced by this plant should be less than or equal to 450. Now the total number of units of good at Plant 1 is simply just x11 plus x12, right? So x11 plus x12 should be less than 450. Likewise, for Plant 2, x21 plus x22 should be less than 600. Same thing goes for Plant 3, x31 plus x32 is less than 380. And this should limit the capacity of the plants. Likewise, if we go to the customer table, we can see that the total number of goods served to customer 1 should be equal to 300. So for that, let's go ahead and say y11, which is the total number of goods transported from warehouse 1 to customer 1, and y21 plus y21, this is the total number of goods given to customer 1, should be equal to 300. Let's go on to customer 2, customer 3, and customer 4. So I don't like how this looks like a lot of variables double indexed. We could simply rename our variables as we wish. So I'm going to name this as I'll name this variable as x1, this as x2, x3, x4. Notice that those x's are indexed by one number. It's not a double index, it's not a matrix. You can see it as a vector. y11 could be set to x7 so that things are consecutive. This is x8, x9, 10, all the way down to 14, right? Got 14 variables up to this point. If we want to do the link right here, so this guy is x1, this is x2, this is x3, 4, 5, and a 6, this is 7, this is 11, this is 8, this is 12, 9 and 13, 10 and 14, right? We can recopy everything right here. So at this point, my problem looks like this. It's not done yet. I'm just saying we can reformulate it that way. So this is how the problem looks like right now. It's not done. We're still missing a really important point right now. And it's the idea of supply and demand. So that said, all intermediate nodes should act as, you could see all the goods conserved. That said, everything that is coming in should go out. The warehouses should not lose. Ideally, they shouldn't lose any items unless the warehouse sucks or there's thieves around in the neighborhood or whatsoever reason. But ideally, warehouses should not lose goods. That statement will give two additional constraints. Each constraint is associated to a warehouse. All the goods that are going inside warehouse 1 should be given back or shipped to all the customers. Likewise, everything that came into warehouse 2 should leave warehouse 2. So everything leaving warehouse 1 is y11 plus all the way down to y14, right? Minus everything coming into warehouse 1 is x11 should be set to 0. Now, remember that we did some sort of mapping between xi's and the uppercase xij, yij. So replacing those here, this guy is x7, x8, x9, x10, and x1, x3, x5. This is x11, x12, 13, 14, and this is x2, x4, and x6. Now adding those two constraints to the problem will give me following two additional constraints, right? So this is the problem we have. First of all, let's recognize that this is a linear program, right? This could be written as C transpose X, right? Those three inequality constraints could be written as AX less than B. I'm going to insert a subscript here, AI, BI, that stands for inequality, and the rest can be written as AX equal to B. I'll just insert a subscript E, standing for equality. Okay? So how do we formulate those matrices and vectors? So first of all, my C should look something like this. 4, 7, I'll just copy paste the coefficients right here, 4, 7, 8, 5, right? My AI matrix should look something like this. So 1, 1 as for x1, x2, and the rest are zeros. And I've got a 0, 0, 1, 1, 0, and the rest are zeros. And likewise 0, 0, 0, 0, 1, 1, 0, and the rest are zeros. My BI is clearly the right-hand side for 50, 600, and 380. And in a very similar manner, we could fill in AE and BE. The reason I'm filling those matrices up is that I'm going to solve this right now on MATLAB. And I've got a script here called Transshipment 1. It's empty, obviously. So first of all, let me go ahead and define my vector C, which was here. I'll just copy the values. Then I have to copy my AI and BI. Let's say AI is of size 3 by 14, right? 14 variables, 3 constraints. Now in the first row, we've got, as you can see here, in the first row, we've got the first and the second entries equal to 1. So we can write it as such. Copy paste this twice more. And here we've got the third and fourth, as you can see, and the fifth and the sixth. So here, as we can see, the second row, only the third and fourth columns are set to 1. Likewise, in the third row, the fifth and sixth column are set to 1. So don't forget to set this to 2 and set this to 3. Run, type in AI, and this is your matrix AI. Okay. Likewise, I'm going to find my BI just by copying those values right here. 450, 600, and 380. Now, let's form AE and BE. As we said, we can form them in the same way as AI and BI, right? So AE is a matrix with, let's see how many constraints do we have. We've got 1, 2, 3, 4, 5, and 6. So we've got 6 constraints and 14 number of variables. Now I'm going to define here n bar, which is 14 because I don't want to keep typing 14 over and over again. So n bar and n bar, right? Now in AE, in the first constraint, which is this guy, only the 7th and 11th columns or variables or coefficients of the variables, to be more precise, are 1. So in the first row and the 7th, 11th column of matrix AE, it is 1, and else we've got zeros. So 7, 11, we set it to 1. Next, I'm going to copy paste this 1, 2, 3, 4. So 3 more times because this, and this constraint look the same, right? So I'll just copy paste it 3 more times. And here I've got a 2 and a 3 and a 4. This guy is an 8. This is a 12. This guy is a 9. This is a 13. This guy is a 10. And this is a 14, right? Now let's go to the supply and demand constraints. So this guy, first of all. So in the fifth constraint, or what are the entries that should be set to 1? There are 7, 8, 9, and 10. So I'll go here and say 7 till 10, right, are set to 1. And we've got 1, 3, and 5 set to minus 1. So 1, 3, and 5, just set them to minus 1, right? I'll copy paste this here. So in the sixth constraint, I've got 11 down to 14 set to 1. So 11 and 14 are set to 1. Whereas 2, 4, and 6 are set to minus 1. 2, 4, and 6 are set to minus 1. So this is my AE, as simple as that. And my BE vector is just the right hand side right here. So it's 300, 300, 400, 0, 0. Now we are ready to solve our problem using the linprog. So the linear programming function of MATLAB. I'll just pass it here the vector C, matrix AE, vector BE, and the lower bound and upper bound on X. So the lower bound on X, let's set it to zeros because all my Xi's are positive. So that's a lower bound on X. And the upper bound is just, something that you'd want to set. And this is really important. So this, you have to tweak it a bit because if you set it too low, you might not solve the problem. You might hit the boundary, right? So let's set it to something big for the moment. It's set uniformly to 100,000 throughout all my variables. Going back to the linprog right here, so we've inputted almost everything. Some optional stuff are left, like the initial point where you want to start. I'll set this to empty because I don't know where I want to start. And the options, right? Some options. So in the options, you'd want to define here some properties and corresponding values. So we're using linprog, and the algorithm we'd like to use is you can use the dual simplex. And I'd like to display what's going on at every iteration, right? So this is what I've got. Okay, let's run this. Optimal solution found. Okay, what is it? We've got a semicolon right here. Right here, let me remove it. So run. And here's my optimal solution. This is the optimal value of the problem. P star, in case you've been watching my convex optimization course, we refer to this as P star and this as X star, right? So we just copied the values right here along with the initial labeling, xij's and yij's, right? So there's a nice interpretation right here, which is the following. First of all, plant 1, actually, all 3 plants are storing their goods only in one warehouse. They're not distributing their goods among warehouses because according to the optimal solution, this is not necessary. If we take a look at X1 and X2, we see that plant 1 stores all its capacity, 450, which is the total capacity right here, in warehouse 1, right? Plant 2 stores its entire capacity in warehouse 2. And plant 3 stores 250 in warehouse 1, which is not the entire capacity. The capacity right here was 380. So warehouse 3 didn't reach its maximum manufacturing limit, let's put it that way. Whereas plants 1 and 2 did, right? So this is not maximum. Now, if we take a look at the other transportation problem, warehouse towards the customers, we see another very interesting thing, which is that warehouse 1, if we take a look at this, customer 1 gets all its goods from warehouse 2. It's not split among warehouses, warehouse 1 and 2. No, it gets all its demand from warehouse 2. Same goes to customer 3, who gets all his demand from warehouse 2, and customers 2 and 4 get their entire demand from warehouse 1. That's a very nice interpretation. Now, another important thing is P star of the problem. So P star right here was, go back to MATLAB, it's this number right here. It's 1.185 E4, means it's 11,850. So this is the minimum cost according to this modeling. Now, let's take another case. Let's say customer 4 right here is a special customer. Okay. Let's say this customer has some sort of deal with plan 3. So plan 3 is ready to ship towards customer 4 at a special cost. Put it that way. And what is this cost? Let's say it costs, I don't know, $7 per unit to ship from plan 3 to customer 4. Now, how do we embed this into the problem that we have? So some simple manipulations could be done. It's not a big deal. So we can just come here and add a plus 7x15, where x15 is the number of units moved towards customer 4 thanks to plan 3. Okay. Now, does x15 show up in the constraints? Of course it does. How? Well, if this constraint corresponds to plan 3, it means it has to take into account x15. So this constraint should be written as x5 plus x6 plus x15 should be less than 380. Because now plan 3 is willing to take into account customer 4. Does it show up in the supply and demand constraints? Well, no, it doesn't, because there's no arrow going into the warehouses. Because, let's put it that way, there's no goods through this path. This path doesn't pass through any of those warehouses. So those two constraints are left untouched. This and this. Okay, so now, do we have another solution to the problem? Well, of course we do. Well, at least we have another x15 right here. So let's see the solution of this problem on MATLAB. I created another empty script called Transshipment 2. Just copy paste the code that I had in Transshipment 1 because we're going to do some minor modifications. So I have one more variable, so plus 1, and my C, we're just going to append the C by a value 7 due to 7x15. So 7 right here. And we're going to modify the third constraint by adding x15 over here. So this constraint right here, I'll add a 15, and that's basically it. So run. So this guy is the optimal solution. This is the optimal value. I copy pasted them here. And as we can see, we have the same optimal values for x1 down to x14, and x15 is set to 0, leading to the same optimal value. So what does that mean? It means that opening a special path for customer 4 via plan 3 is useless. It doesn't improve or reduce the cost. It doesn't change the effect of other paths. No, this is completely useless. Okay, let's go back to MATLAB. Now, what if, now that is a bit fictitious, but what if plan 3 was willing to pay customer 4 for transportation? That's a bit fictitious. Will that change everything? Well, yes. As we can see, x15 is now 130. So the customer is willing to open this path. Simple as that. Now let's do a bit of a twist right here. Now let's say the two warehouses interact. What does that mean? It means that they're permitted to exchange goods between each other, warehouses, right, at a certain cost. So this arises, let's say one warehouse is, I don't know, maybe saturated. So it's willing to send its goods to another warehouse at a certain cost. Now let's say the cost to go from warehouse 1 to 2 is 2 per unit. Likewise, to go from 2 to 1 is also 2. Okay? Now we're going to model this via decision variables x16 and x17, because up till now we have 15 variables, and this is going to change the problem as such. So we said 2 for 16 and 2 for 17. And is this going to change anything about the plants? Any constraints on the plants? Well, no, because this interaction is not directly related, let's say, with the plants, so it doesn't enter at least those 3 constraints. Does it enter those 4 constraints, the customer constraints? No, it doesn't. Again, due to the same reason. There's no direct interaction between this exchange between warehouse 1 and 2. Now, does it enter in those last 2 constraints? Well, yes, it does. How? As we said, no warehouse is willing to lose goods, which also includes the path from 1 till 2 and 2 till 1. So if you write those 2 equations down again, warehouse 1 and warehouse 2, with x16 and x17, you will see that we're going to have a minus x16 right here and a minus x17 just over here. Okay, let's create another script, call it Transshipment 3, to solve this new problem. I'll copy paste everything I had in Transshipment 2 because we're going to do some minor modifications. Namely, the number of variables are now augmented by 2. The C vector right here is appended by 2 twice, so 2, 2. And the last 2 equality constraints, namely the one in AE, those are modified. How? x16 enters as such with the minus sign, so here I've got a 16 and here I've got a 17, right? So this is what I have right now. That's it. Let's run this. And as you can see, this is the optimal solution of the problem. So I copied the values right here, just next to the 2 preceding situations. I'll also copy the optimal value of the problem. So E star right here is 8,400. Less than those 2. Now let's look at the optimal solution a bit. It's super logical and the strategy is not realistic. Why? It's because plants are not allowed to, well, they will not send any of their goods to any of the warehouses. More than that, we can see that Y12, Y14, Y21, and Y23 are left untouched. So that said, customers still get their goods from the same warehouses. And let's see what's going on right here. It's that warehouses are exchanging goods between each other. So the optimal solution tells the warehouses do not get any goods from the plants. This is not good. And the reason why is because the path right here is super cheap. It's 2. It's cheaper than any other path. So that will favor warehouse 1 to ask goods from warehouse 2 and vice versa. If this is true, then let's take a look at the other extreme case. What if these costs were extremely high? What would happen? Well, I think, before running any simulation, I think if those 2 paths were really high, then x16 and x17 will be 0. That means that warehouses will not exchange between each other because it's super expensive, and all the other values tend to go to their initial values where exchanging is not present between warehouses. That is, x1 will be 450, x4 will be 600, x5 will be 250. Let's check this for a moment. So the way we can do this is just modify 2 and 2 right here. Let's say to values such as 10 and 10. So that means that warehouses, it costs $10 per unit to exchange from warehouse 1 till 2 and vice versa. So running this, and there you go. x16 and x17 are 0. Other values are reset back to their original values. Okay? Well, let's do some of a change right here. Let's put this to 10 and this to 2. Run. And there you have it. So because it is super expensive to go from warehouse 1 till 2, well, warehouse 1 will not move any goods to warehouse 2. Whereas warehouse 2 will move 850 units to warehouse 1. As you can see right here, it's only plant 1 that is moving to warehouse 1. It will move nothing to warehouse 2 because there's a very cheap path going from 2 to 1. So why bother and move till 2, right? We'll move them all to 1 and that's it. So let's put something in between value, 5 and 5, run. 5 is still super expensive according to the system. Run. So 4 and 4. 4 is cheap. Put 4.5. 4.5 is cheap. 4.8 maybe. This is also cheap. 0.99. This is also cheap. So 5 is at the limit. So at 5 exactly, it's as if the interaction is not there. Okay? So yeah, that's basically it for this mini lesson on the transshipment problem. We modeled a really cool example. Industries moving or plants moving towards warehouses, and warehouses then shipping to customers. We saw edge cases where plants are allowed to cheat, let's put it that way. They have special clients or customers, and they're allowed to move some of their goods by this path. In this case, has no effect on the problem, whereas in other cases, it indeed has. We also saw that interaction might or might not help, depending on the cost of their path. We saw how to model this type of problem as a linear program and how to solve it easily on MATLAB. Thanks for watching. If you found this application really useful, please consider subscribing to this channel and liking this video. If you have any questions, just comment down in the comment section below, and I'll be seeing you in future videos.